All right, guys, we're going to get going on this. Let me start where we had finished off before. So I had expressed that the internal energy is equal to 3/2 nRT, and with that, there's another way of expressing that internal energy that I neglected. That the equation is actually on the FRQ sheet, and so I want to present that to you. And here that is. This is the equation as written on the FRQ equation sheet. K is that sort of average kinetic energy, which is the same thing as that internal energy. So we have the 3/2 K times T. The K is known as Boltzmann's constant, and this is a constant value that is also on that AP test equation sheet. So this is your temperature in kelvins, and the K is measured in joules. Don't confuse this K with like Coulomb's constant, right? The Coulomb's law constant, that's different. Don't confuse them, but they are different. Okay. Any questions on that? Yes.
There's no moles in that one.
No moles. In fact, all right. So my statement is, I'm going to look a little bit more into that to be able to say that a little bit more confidently in terms of whether it's energy total or energy per molecule. But I'm actually looking at it a little bit differently now that you asked that, and I'll have to look at an example question for us to answer in order to. So I'll come up with something. All right. So let me move on because I'll move on and we'll deal with that later. So my fault. But we'll hit that later. All right. Nonetheless, I'm going to look at some atomic theory and then we're going to move on to nuclear theory. So by atomic theory, I'm going to deal basically with electrons and energy levels. With chemistry, you described like orbitals and things like that, but we're going to be talking about energy levels specifically. So if we're going to look at the Bohr model, she's not a really boring lady.
There's the door.
You would lock me out. Okay, so the Bohr. All right. What Niels Bohr said was that the angular momentum P of an electron, right? Of an electron, that was an attempt at an E there. So the momentum of an electron is quantized. And so by saying that, it's quantized, meaning that it jumps up discrete levels. It doesn't go up any. It's almost like, if you guys understand the difference between like digital and analog, I almost look at it like it's digital in that way. It goes up discrete absolute levels. So that brings us to the principal quantum number, right? What's known as the principal quantum number. Right, so we're looking at n is equal to 1, 2, 3, and so on. So that's our principal quantum number. What he had said, and if I can move this up a little bit, what he had said is that the angular momentum L, remember that L is angular momentum, which is really annoying actually, but it just is equal to mvr for an electron. And we can show through rotational and circular motion why that is. If you want me to, I can derive that. Okay. It's actually not terribly complex. It would be a good review, but nonetheless. Let me just express it. So NH over 2 pi is what he had said. And so that was one thing that he had said. And so this part here, I'm not deriving. I'm not getting there. I'm not even messing with it. I don't know that I could. But this I can.
You can do it.
All right, so if you want me to, I can take care of that. I've got this. I've got the angular momentum is equal to omega I. That is the angular velocity times its moment of inertia, or rotational inertia, whichever you prefer to use in terms of terminology. So that is a given. And then the inertia at standard is mr squared. So if I replace mr squared for the I, I'm going to take this and insert that into there. So I've got L is actually equal to little omega times mr squared. And let's see here. Remember that R is our Rosetta Stone. It's our translator between linear and angular motion. So linear velocity along the tangent is equal to omega R. And since that's true, then I can divide each side by R and say that the angular velocity is equal to the linear velocity divided by R. So I'm going to take this and substitute that in to there. So I've got the angular momentum is equal to V over R times mr squared. And you will notice that one of the r's will cancel out. So that is L is equal to V m r. And that is where I start. That is velocity. So it's too big. It's too big. I'm sorry. Okay. A curtsy is in order. Okay, so moving on, nonetheless, nice quick little review. We're good on that. So we've established that this is in fact equal to angular momentum, and he is saying that this is in turn equal to that up there, and I will go back up and kind of establish that a little bit better if I can. That I'm not deriving. I told you I'm not. Because it's above my pay grade. So, N, what all that really matters, okay, is N is the number of moles. H is Planck's constant, which is a constant that you will find on the paper. So if we look for constants, I know it's there somewhere, Planck's constant. It expresses it in terms of two different units. By the way, they express it in two different units, and you need to be ready to use it in either one of these two, which kind of sucks, but it is. So here is what Planck's constant is. H, Planck's constant. Let me write that out. Planck's constant is equal to 6.63 times 10 to the negative 34 joules times seconds. And if I'm not mistaken, it has other units to it as well. That is also equal to the same thing as meters squared times kilograms divided by seconds.
But it's still the same number.
Yes. These two units are the same. Yeah, right. It's just I want to make that aware because I was, a couple of nights ago, I was kind of looking through solving some practice problems, and by looking at the units this way, it became more obvious that I should use this number versus the other number. So that's why I'm expressing it that way, that it's nice to realize, you know, yes, you're right, you should be able to derive that and come to that realization that these two things are the same.
Do it.
can I move on for now and maybe come back to it later? The other number is 4.14 times 10 to the negative 15th. And this is, rather than joules, it is going to be a value of electron volts times seconds. All right, so basically what it comes down to is if your problem is dealing with electron volts, you might have to use that number instead. But if you're dealing with meters and joules or whatever it may be, then use the top number. So these are your two different values for Planck's constant, 6.63 times 10 to the negative 34th, or 4.14 times 10 to the negative 15th. All right, so with that said, let's move on. Just have that kind of put that away and let me express the energy of an electron at any particular energy level n, or n at any quantum number n. And I'm going to give you kind of a long equation here, but we're going to take a look at it.
Ooh, are you taking this lecture?
Yep.
Okay, yeah.
Wait, what?
Are you taking this lecture?
Yes.
Hi, people listening to the lecture. My name's George.
Just because of people who aren't here for this.
Yeah, I'll probably edit it and whatnot, but I'll keep in the applause. Thank you. I'm sorry. Would it be really cheesy if I said I live for the applause? Applause. Okay. No. All right. So this is the energy of an electron at any particular energy level. The K in this case, the K is Coulomb's law constant. Because we're not dealing with heat, it is not Boltzmann's constant. That's heat, right? This is almost a good opportunity for me to be like, hey, here's the same variable that we see in the same day, like you're going to see on the test, right? But I need you to be aware that they use the same letter for different things. What is the topic? Okay? Don't get them confused. So Boltzmann's constant is for heat and thermo stuff. Coulomb's law is used for electrostatics, obviously, and it's also going to be used for, well, it's electrons. It's still electrostatics. Okay? So stick with me there. So that is Coulomb's law constant. Please don't. And E is the charge of an electron, M is the mass of that electron, and H is Planck's constant. For hydrogen. Yes.
Is the thing under, like, square and the denominator, is that an H?
This is an H for Planck's constant,
Okay. Because I thought it was,
and this is an N.
and I was like, wait, why did you?
No, this is an H. Sorry if I didn't extend my little thing enough. So for hydrogen, which is virtually almost always going to be the case, you're going to talk either about hydrogen or helium, right? I mean, that's just the way it's always going to be. So hydrogen has one proton, one electron, so we're going to talk about hydrogen. And for hydrogen specifically, E sub n is equal to negative 13.6. I'll have to look up as to why it's a negative. I guess I didn't really question it when I was looking at it the first time. So negative 13.6 electron volts, I think it's simply because it's an electron. It's negatively charged, but I don't know if there's any other reason other than that. And that's over n squared. And that is going to be a value of an electron volt. So it's 13.6 electron volts over n squared. And so that right there can simplify things as long as we're just looking at hydrogen. And so from there, let me move this to the side. energy levels. So here's, let's say this is n equals 1. Here we've got n equals 2, n equals 3, and so on. So I'll probably stop at n equals 4, but you could have, and what the heck, we'll do n equals 5, right? So you can have these energy levels, and we can make a couple of statements. If you have an electron at some energy level, let's say I'm going to draw in an electron, and it's going to jump up energy levels. So in order for it to jump up an energy level, and we're going to have a little bit of fun with this. Oh, that didn't work at all. Let's try that again. All right, so here's my little photon, right? Hits the electron and bumps it up an energy level. Let's say that it's enough energy in that photon to bump it up an energy level. The energy of this photon is going to be equal to the change in energy for that electron. Is that pretty clear and fair to say? All right. And then let's say that an electron jumps, or drops, I should say, energy levels. So it goes from, let's say, 3 down to 1, and it releases a photon, and that photon goes off into space and whatever. Then the change in energy levels is equal to the photon it releases. The n equals 1, this is known as the ground state, like the ground floor. So that's known as the ground state. The energy needed, so let me abbreviate it a little bit and say that the E, the energy, I won't abbreviate. The energy needed to free an electron from the atom. What's the question?
Is that the same as the E and
The energy needed to free the electron of an atom is known as the ionization energy. That is known as the ionization energy. So that is our statement, our definition of ionization energy. The energy needed to actually release it. So let's say, for example, that this photon comes in. Whatever's going on with this photon, there we go. This photon comes in, and it's some sort of very high energy photon. Comes in and hits this electron and bumps it up a couple of energy levels. Then this thing comes in, hits it, and then it's gone. It's left the atom completely. The amount of energy that this photon had, the amount of energy it needed to make that happen, is known as the ionization energy. Think of it like escape velocity, right? If I have something that's a terrestrial object, and there's some amount of velocity that it needs to have in order to leave orbit, or to leave the gravitational floor, which is basically 8,000 meters per second for Earth. That's the escape velocity. Think of it in the same sort of way. There's some sort of escape energy needed in order to bump it up past all the energy levels and get it to escape the atom completely. All right, I'm going to make another statement that goes along with the this idea that the wavelength that comes in is going to be equal to that change in energy levels. Let me get my electron back over here. Get back over here. And I'm going to make this statement in terms of an equation. In fact, let me grab my stuff here and pull it down a little. So here's my equation. I'm going to state it this way, that the wavelength of that light, of that photon, is going to be equal to hc over delta E. It's equal to the change in energy of that electron. Or you could express it this way, and if I'm not mistaken, in the, I'll check it, in the AP test, or the equation sheet, I believe it's expressed as that the change in energy is equal to hc over wavelength. Either way is the same, right? In fact, let me... nonetheless, that equation is not on the equation sheet, but nonetheless, it will be useful to have that and to know how to drive to it. All right, in fact, let's say this. All right, so we'll come back to that. And let me make this statement. The absolute value of the change in energy is, for hydrogen, going to be equal to 13.6 times 1 over the final energy level squared. I should put that in the subscript, excuse me. And that's going to be measured in electron volts. Okay, that's going to be measured in electron volts. Let me put that in a different color so that you understand that's not part of the equation. It's just the units for it. That's going to be measured in electron volts. So let's see if we can ask this question and get this answered. The question is this. What is the energy of a photon that is released from an electron that goes from energy level 5 to energy level 2? So what is the energy of the photon when the electron goes from n equals 5 to n equals 2? So there's my question, there's my statement, and you should have all the information you need to answer that question. All right, so it's really not too complex. This is going to be equal to, actually, let me grab this and group it together so that way I can make it a bit smaller. So here's our question, and let me do the work. We have 13.6 times 1 over, let's see, the final energy level is 2, so that's 2 squared, minus 1 over the initial energy, which is 5, so 5 squared, and when you plug that in, you will get a value of 2.86. So that is 2.86 electron volts. You actually don't really need any of the constants when you use this equation, although if you wanted to, we could certainly make it a bit more complex from what we had earlier and derive from there, but we don't want to. So let's do this. We have 2.86 electron volts. Now what I want to know is what is the wavelength? What is the wavelength? So if this is the energy, what is the wavelength? And just due to time, we're going to express it in this way, where wavelength is equal to hc over the change in energy. This is going to be the equation that we want to use. And by putting in HC, H is Planck's constant. You guys all recognize what C is, right? Speed of light, 300 million meters per second. 3.0 times 10 to the 8th meters per second. And E is that energy. So that's going to be the 2.86 electron volts. And when we plug it away, we will have a value of wavelength is going to equal 4.34 times 10 to the negative 7th meters.
I'm confused. Because
So we need to use the 4.14 times 10 to the negative 15th electron volts times seconds for Planck's constant. Because this here is being measured in electron volts, so we have to match that unit with this equation. So the H must be also in electron volts times seconds. So with that said, that will come up to 3.34 times 10 to the negative 7th. And the thing is that we typically measure photons of visible light in terms of nanometers. So how many nanometers is that? One meter is equal to 1.0 times 10 to the negative 9th. I'm sorry, I got that backwards. 1 nanometer is equal to that many meters. Excuse me. So 1 nanometer is equal to 1.0 times 10 to the negative 9th meters. That's the conversion between the two. This is a number, right? This is a conversion that you really should know. It will help you to know it and have that memorized, to be able to move the decimal point that many zeros. We are going to have a value of, I would say that it's 434 nanometers. It's the same thing as 434 times 10 to the negative 9th. So it is 434 nanometers. That is typically going to be the way it's asked. It's going to be asking you in nanometers, so you should make that conversion. Violet. It's going to be violet blue. Violet is about 400 nanometers. Blue, it becomes blue at around 440, 450. So visible light, these are numbers that you should memorize. Visible light ranges somewhere between 400 and 700 nanometers. It actually goes a little bit past that range slightly, but that's basically what it is. It's 400 to 700 nanometers. Okay, so this is going to be violet light. Red light is 700 nanometers. Remember the green laser? The green laser was 530 nanometers. The red laser that we used was about 630, 660, somewhere in that range. So our perception of red has a reasonable amount of range to it. And I'll probably kind of end things for just about there for the day, and I'll go through, and I'm going to work with this equation tomorrow a bit further and show, because remember, let me say this, let me finish on this statement. Don't forget that this statement comes into play with this general topic. What is the velocity? What if I said this? Speed of light. That is the velocity. So that statement is very helpful to you in this topic. All right? Therefore, you can derive a lot of other things to go along with it. So I'll finish there, and that'll be the end of it.